In this video, we'll talk about what logarithms are and some of the reasons why they are needed. So let's say I was asking you to plot some numbers on a number line. So you're like, okay, I'll draw a number line on this page, and there we go. Let's just wait until we get a number before we start putting numbers on there. So 2, all right. Let's say there's 2 right there. Next number, 4 and 8. Okay, so 2, 4, and then we have the same distance twice again. So like 8. 250, oof, 256, okay. Whoa, dude, how am I supposed to put all of those numbers on a number line? Um, and so, like, it would have been really great of me if I had told you what kind of scale to use in order to put all those numbers on a number line. But even still, even if I had said, all right, let's put this, like, segment your number line off into, like, thousands. Well, if I had done that, sure, the 4096 would have been on one end, and the 2 would have been on the other. But all the other 3 numbers there, the 4 and the 8, and to some extent the 256, would be like basically right on top of each other. And so that doesn't quite work. We need to have some other like mechanism for like specifying what the scale would look like. And we'll talk about what that is in a minute. Here's another reason why logarithms might be needed. So if I asked you to multiply these numbers together, okay, so the numbers are 39,810,717, and we're going to multiply that by 316,227. You could all do this. It would take you a significant amount of time. You would have to go, okay, 7 times 7 is 49, so okay, the 4, 7 times 1 is 7, the 4 comes down, so we got 13, right, hit the 1 there. Or no, it's not, 7 times 1 is 7, so it'll be 11 right here, sorry. Anyway, that would take a long time to do. You could totally do it. And for much of history, like when numbers needed to be multiplied together, like you could think back in terms. I'm thinking in terms of like in the not the Dark Ages, the Middle Ages. So in like time where we had like feudal, we had like the like even back into the Egyptian time period where pyramids were being built and stuff. If you had to multiply numbers together, there were some tricks, but for the most part, it was like this. And we didn't have to, luckily, multiply really large numbers together back then, because everything we were talking about was Earth-based. But then, there was a time, like if you've seen the movie Hidden Figures, they had to multiply very large numbers together. They had to figure out, what were the calculations necessary in order to bring those astronauts home. And it would have been more or less impossible for them to have completed those calculations in the time frame required. And so luckily they had some tools at their disposal, and one of those tools was something called a logarithm. And logarithms, we'll talk a little bit about logarithms in a minute, but if I could just say that 316,227 is the same thing as 10 to the 5.5 power, and I could say that 39,810,717 is the same thing as 10 to the 7.6 power, well then I can know that if I'm multiplying these together, the product is just going to be 10 to the 13.1 power, because this is an exponent rule. I have the same base there, so if I add the exponents, it's 10 to the 13.1 power. And then if I just had some way of knowing what 10 to the 13.1 power is, in fact, it's 12 trillion 589 billion 223 million 604,000 759, if I can read my handwriting. That would be really great, because that took no time at all in order to multiply those together, as opposed to having to do that all by hand. And so there's this guy, his name is John Napier. He's a mathematician, and we owe a lot of what we know about math to him. But no advancement he made is more important than logarithms, and he wasn't the only one thinking about logarithms. In fairness, there was another guy named Joost Bürgi from Switzerland who was kind of doing it at the same time. But we attribute logarithms in large part to John Napier. And basically what he did was he's like, okay, he sat down basically and made these big tables. So there was a table where he could go and say, all right, 316,227, that's the same thing as 10 to the 5.5 power. And this was done by basically doing this math a bunch of times. And kind of looking for patterns and seeing how this all works. And there were tables produced. This is a very long book, a very large table. And same deal for this number, that you could find these values. And then there was another table, which was an anti-logarithm, basically, that went the other way and said, all right, if you have this, what is that equal to? And so you had one table to go one direction, another table to go another direction. And in the time of like hidden figures, for example, that was like in the 1960s. This was before calculators existed. So before we had calculators, even we had like some mechanical ways of calculating things. We had like slide rules and stuff, but we didn't have like it was very difficult and inefficient to multiply large numbers together without the use of logarithms. In that movie Hidden Figures, at several points in the movie, they pull out these huge binders, and these binders they were tables. They were tables where they had known values calculated out. So they had things like these logarithm tables, and they also had trigonometric tables. So the trig ratios of specific angles were also pre-calculated, basically, so they could be used for reference. And it was the work of mathematicians in the past that enabled this. And like since then, like we have pocket calculators. No math teacher should ever make you do this math by hand. Because you could just do that in a calculator in a matter of seconds, as opposed to probably like 20 minutes worth of math that you could make multiple errors on. And so this is the power of a logarithm. And let's now go back to, well, what is a logarithm then? So a logarithm is an exponent. It's the answer to the question, what power of like some base is this number? For example, right, if I had 10 to the x power, so 10 to what power gives me 1,000? 3, right? You could tell me right away that 10 to the third power is 1,000. So the logarithm there is 3. The way it's written is something like this. Log base 10 of 1,000 is what? 10 to what power is 1,000? Well, the third power, right? And you could do this for any number theoretically. Like you don't have to have obvious numbers here. If you had something like log base 3 of 526, right? 3 to what power is 526? Well, this power. 3 to the power of log base 3, 526, that is the power that you have to raise 3 to in order to get to 526. And we'll talk more about this in the future, but let's go back to that. Let's go back to, so just to be clear, like if the answer this is an exponent and this is the answer, this is the logarithm, right? So a logarithm is an exponent. It goes in the exponent of some base. If I went back to this question and I said, all right, plot these numbers on a number line, well, we could look at this in a logarithm perspective. If I had n right here, and this was log base 2 of n, like say I want to know 2 to what power gives me these numbers, well, I could say, so if n, so n are these numbers I've given here, so 2, right? 2 to what power is 2? 1, right? 4, 2 to what power is 4? The second power. Log base 2 of 4. What power? Log base 2 of 4. What power do I have to raise 2 to in order to get to 4? 2, the second power, right? 8, this would be 3. If I don't have it on here, but 16, that would be to the 4th power. 256, that's 2 to the 8th. So the logarithm would be 8. Now, if I wanted to figure out if I had to say I didn't know say I didn't know that 2 to the 12th power was 4,096, I could use logarithms real quick to figure that out, because look, I know that 16 times 12 is 4,096. So I could say, well, this is 2 to the 4th, and this is 2 to the 8th. So if I add the 4 and the 8, ooh, okay, cool. So 4,096, that's 2 to the 12th power. Or, no, I don't write that there, sorry, I just write 12. Okay, so if I wanted to plot these numbers on a number line now, I could do it. Because if I would just put 1, I'd have, I had 2 on there. There's 3. Okay, then I had like 8, so it's somewhere over here or whatever, and I had 12, it's reasonable, it's right there. And then I would have to specify that this is a log base 2 scale, like this is, it's a logarithmic scale of base 2. So now it's totally doable. Now let's just define a couple things about a logarithm real quick. So here's what a logarithm looks like. It's this one right here. Okay, so how we say this is log base b of n is equal to p, or b to what power gives me n. And so here's an example, right? If I had log base 2 of 3, oops, sorry. I don't know how to write letters. Let's say log base, I don't know, 3 of 27. So 3 to what power gives me 27? 3 to the 3rd power gives me 27. If I didn't know, like let's say I wanted to log base 3 of I don't know, 516. I don't know what that was. That's the same thing as saying 3 to what power, right? What power gives me 516? I don't know. The answer is log base 3 of 516. That's what power I'd have to raise 3 to in order to get 516. So we will talk more about how you go about, so first of all, we'll talk more about what are the limitations to this, and also how do you do this? How do you go from one of these to the other? There's a very simple, powerful trick that you can do, because if you just were trying to memorize these two things here and how you can convert from one to the other, that can be difficult to memorize that. Instead, there's a technique that works every time. And so we'll talk about that in the next video.